We've got plenty of time and space for our invited speaker, SEO's very own Micky Maganini. I'm so happy to provide some time, some space. I know you've been working in this sector for a long time on really not only curriculum development, but also sort of uniting these practices for these good practices for data collection, training data, and machine learning oriented data. So it's really exciting. And I know this is a sort of a new format to how we generally do some of the presentations. This is going to be more of a discussion forum. So really excited because I know we've got 23 people on the line who all work in this space and are really sort of interested in not only the different concepts, but also sort of the good practices, as I had mentioned. So you've got a couple of Jamboards here, which we'll link in some slides as well. And all this material is going to be found on our website at the very end. So as always, if you can't catch it now, you can catch it later. And Biplav, I don't know if you've already kicked off the recording. If not, well, we can go ahead and launch it. And Then I'll hand it over to Micky. The floor is yours. I'll stop presenting.
All right, thank you very much. Yeah, so I'm going to start with a quick presentation just to make sure we're all on the same page as far as terminology goes, and then we'll get started with the discussion. So yeah, today I wanted to host a discussion regarding the best practices for creating a land cover map using machine learning, but we also are welcoming perspectives outside of just land cover. So any perspectives regarding the collection of training and validation data with regards to machine learning. And we're also going to talk about data preparation, what are the best practices for a practitioner who wants to prepare their Earth observation data to be used in a machine learning classifier. So first of all, I just wanted to thank Tim and Biplav for providing me space in the really crowded schedule. I really appreciate it. We've heard a lot of great presentations in the past couple of weeks in the Geo-AI working group regarding these new foundational models and all of this awesome work that's being done with regards to model architecture. But I wanted to take a step away from that today and talk about collecting training data, because at the end of the day, we still need reference data to train and to validate these algorithms. So the idea to have this discussion first began when I was developing educational materials regarding SERVIR's tool, Collect Earth Online. And that's a tool that helps you to create image interpretation projects and also allows you to view Earth observation data while you're doing so. And while I was creating these materials, I was asking myself all kinds of questions about, okay, well, what are the best practices for actually collecting this data? Is there a standardized framework for collecting this data to be given to a machine learning classifier? So that's what we're going to walk through today. A lot of these questions I have are still unanswered 2 years later. As you can see, I work in the weather and climate resilience thematic area. I don't work as much with land cover, so I'm sort of relying on the expertise of you all to help answer these questions. So I'm going to start with a brief presentation, but at any moment, please feel free to unmute yourself and interject. I can't see the meeting tab right now, so Tim and Biplav, please interrupt and moderate the chat if you could. That would be awesome. So I think I covered everything. So as I said before, we'll start with a brief presentation on the terminology of image interpretation projects that will help make sure we're all on the same page. And then I have a Jamboard prepared, which I believe is linked in the chat, that we'll walk through together and sort of discuss these questions one by one. So first, let's start with this crash course on what is an image interpretation project and what are the different components of it. So an image interpretation project refers to collecting a set of Earth observation imagery and then making observations about the land cover class at various locations within that imagery. And there's two main types of image interpretation projects that people use a platform like Collect Earth Online for. So the first is a sample-based inventory where we're taking a look at a small portion of the region of interest and making conclusions about that small portion and then applying those conclusions to the region at large. But what I imagine this group is more interested is in the training and or validation of a land cover map using machine learning. And that's really what SERVIR uses a lot of our image interpretation projects to do. So we collect data about a small portion of our region of interest, then we train an algorithm based on the manual classifications that we arrived at in that data. And then we can also validate that algorithm using a separate image interpretation project. So what are the components of an image interpretation project? So in creating these educational materials for collectors online, I found these this set of terminology that's following Dr. Stamen, who is nice enough to join the call today. Thank you for being here. From his paper with Dr. Chapluski in 1998. So there's two components of an image interpretation project, which are sampling design and response design. And so sampling design refers to how we're going to distribute samples within our region of interest. And then at each of those samples, we're going to make a manual classification about the land covered class that we're seeing. And then the response design refers to it refers to the set of rules that we're going to follow when we're classifying each of those samples as a certain land cover class. So within the sampling design, there's many decisions that you have to make as a practitioner. You have to decide the sample size, how many points you're going to allocate as a whole. And then you also might want to use what's called strata or clusters in your sampling design. So strata just refer to groups of pixels that are both exhaustive and exclusive. So that simply means that every pixel within your region of interest can be assigned to one and only one strata. And commonly what we'll do for our strata is to use land cover itself as a strata. So if you want to make a land cover map using a machine learning classifier, you might want to take a pre-existing land cover map and use that as your strata to make sure you're collecting samples from a wide variety of land cover classes. That way your model knows what each land cover class in your region of interest looks like. So that's strata, and then we also have clusters. So clusters are manually defined groups of pixels within your study area that you can see an example of on the top right. So these are really helpful if you're validating an existing land cover product because you might be dealing with clouds. You might want to use high resolution optical imagery to validate your land cover product, but you have to work around these clouds. So oftentimes people will use clusters to identify the regions in the area of interest that do not have cloud cover and sort of manually create clusters in there. So you can have strata, you can have clusters, you can have both. And then this allocation term refers to how you're actually going to go about distributing these samples within these strata or within those clusters. So there's equal allocation where you distribute your sample size evenly across those strata. And then there is proportional allocation where you're allocating a larger number of samples to dominant land cover classes that occupy a larger area, and you're allocating less samples to those that occupy only a small area. And then you have hybrid allocation like the ones proposed in Dr. Olafson's paper in 2014, where you assign a set number of samples to each land cover class, and then from there you undergo a proportional allocation. So there's all these different decisions you have to make when designing your sampling design, which we'll discuss soon. And then there's also the response design, which is how you're actually going to classify those samples at each location. So the assessment unit refers to the area that you're going to consider at each point sample when making the conclusion about that assessment unit. And then the selection protocol refers to the set of rules that you are going to abide by when you're manually classifying each assessment unit. So let's say this is our assessment unit in the bottom right here, and 60% of this pixel or assessment unit rather is covered in water, and the other 40% is covered by tree cover. What are we going to classify that assessment unit as? So these are the types of questions that we're going to ask ourselves: is there a standardized way is there a standardized selection protocol that we want to use when we are collecting training data for a machine learning algorithm, or does it really depend on the case? Is it a case-by-case basis? And you can also see an example of simple random sampling versus stratified random sampling in the bottom left here. And then finally, we also have a classification schema as a component of our image interpretation project, which is just each land cover class that we're going to consider when we're classifying our project. So I'd like to pause really quickly here if there's any questions about image interpretation projects and all of the jargon that I just threw at you. But if not, we can go ahead and move to the Jamboard and start with the discussion. So seeing no questions, I'll link the Jamboard in the chat. I'm not sure if it's already there, and I'll switch over to that.
I just added it, Mickey.
Thank you very much. So I'll stop presenting this tab and go over to the Jamboard. So I, of course, cheated. I had time ahead of time to think about these questions and go through the literature and add my, what I've found as not answers to these questions, but perspectives with regards to these questions. But I'd really welcome anybody to add their own sticky note. You can do that by first opening this link and then clicking sticky note on the left. And then if you could just type your name and your organization before giving your 2 cents, that would be awesome. And then also, if you'd rather just speak up about any of my perspectives, or you disagree, or you have some other papers that the group might be interested in, please go ahead and speak up at any time. So the first question I had is, what is probably the first question that you're going to have when you're creating an image interpretation project is, what should my sample size be? So in the literature, I found 2 perspectives for this, and these apply only to traditional machine learning classifiers like random forest. So I have no clue how this applies to foundational models or any sort of the newer architectures that are being developed. But what I found is that there's 2 main methods in the community for determining your training data sample size. The first has to do with these top 4 sticky notes here, and it's sort of a statistical way to determine what your training data sample size should be. And it's based on what you want, how accurate essentially you want your product to be. And then the second method, which is a simpler method that I've used, is that it's called a heuristic method. I'm not sure if I'm pronouncing that correctly, but it advises that you should collect between 10 and 30 samples per band used in the classifier. So if you're just using optical imagery, you're just using red, green, and blue, you would collect between 10 and 30 times 3, so between 30 and 90 samples for each class, for each land cover class. So not seeing any other perspectives or thoughts there. Or Tim, I saw you just posted one. If you wanted to speak to that, please go ahead.
Yeah, I'll get the conversation just kind of rolling. I mean, I don't have a definitive answer. I feel like it's kind of case by case, and maybe I'm committing a heinous crime here, right? So this is a good area for discussion. But, I feel like the kind of questions I'm always asking myself are, like, what am I predicting, first off? Like, how many classes am I predicting? And what's the proportion of that landscape? So, I mean, a good example is if you're looking at an area that maybe only has 4 pixels in it, it's going to be really challenging already. You're going to sort of violate a lot of rules. But if you're doing the entire globe, that proportion or the number of samples is going to be really important as well. So I don't have a hard and fast rule, but those are the kind of questions I'm asking myself to make sure that I'm not committing any crime. So I'll pause there because I just wanted to get the conversation going. Maybe I'll toss another question out. What are some of the questions you guys are asking yourselves?
Yeah, and I will say a lot of these questions are maybe harder to answer and are just like more rhetorical for when you're designing your project, just something to be thinking about. So if there's no right answer, that's fine too. Yeah, please go ahead, Emil.
Yeah, sure. And I'm not sure if like this is the opportunity to kind of put people on the spot, but having attended a few workshops with Pontus, I know that's a question he often gets. And since he's here in the discussion with us, I didn't know if maybe he might also want to offer some words of wisdom on that in terms of training sample sizes and I guess what is statistically appropriate. Pontus?
Yeah, I think the recommendations in the paper that we wrote in the past, we just simply take the variance estimator for the design that corresponds to the sampling design and solve it for n. And then so that is typically how we do it. And so for simple random sampling, systematic sampling, that's pretty straightforward. For stratified random sampling, it gets a little bit trickier. You have to kind of specify the desired margin of error, right? So typically what we have been doing in like Silva Carbon and SERVIR is that people want to estimate the area of forest change, the area of deforestation or degradation or whatever it might be. And so what we then do is that we specify kind of desired margin of error of the area of interest. And then we kind of plug that into the variance estimator, and that will give us a ballpark number of the number of sample units required to meet that kind of target standard error or target margin of error, if you will. So that's how we've been doing it. And then under stratified random sampling, we then need to figure out how to allocate that sample. And so how many sample units should we draw from each of the strata? And, Steve is here too. So I think typically it depends a little bit on the estimation objective. And Steve, correct me if I'm wrong here, but if we're interested in area and also overall accuracy, producer's accuracy as well, I guess. But typically a common estimation objective is estimate an area. And then we typically want to do something like a proportion allocation. So we allocate a sample size per strata that is proportional to the size of the strata. The problem then is that some strata might be very, very small, and so you end up with a very small sample size. And so we typically just say, then we just bump the sample size up to like 20 or 25 or 30 or something like that. That's typically how we've been doing it. So just trying to keep it very, very simple. Again, you take the variance estimator for the sampling design in question, you solve this for n, and then you plug in a desired margin of error, and that will give you the total sample size, and then try to allocate it as proportional as possible. That's kind of the overall guidance that that we have provided, and I think that is in the 2014 paper that we wrote. That's typically how we've been doing it as well.
Yeah, I think Emil actually just linked that in the chat.
And then
Emil, I also saw you had your hand up.
Yeah, if I could just follow that up with one more question. Also, in terms of the work, Pontus, that you've done in support of our SERVIR hubs through your applied sciences team work, could you also perhaps comment on the Area 2 Google Earth Engine repository that you put together? Just again, because it seems like in terms of actually like implementing that, what you mentioned, like it seems like Area 2 is like a good way to go about that, right?
Yeah, that was an attempt to primarily to draw the sample originally. That people struggle with that. You do everything in Google Earth Engine, and it was kind of clunky to draw a sample under stratified random sampling, for example. So we just tried to write some scripts that would automate that. And then we also implemented the associated estimators. So once you have collected your reference observations. I have observed reference conditions at the sample location. Once that have been recorded, you can then easily apply an estimator to that sample data by clicking a few buttons. And so I think Caitlin Terrio, who's doing most of the work for my SERVIR project, she's been using those set of scripts and some of the trainings that we've been doing in West Africa. But it's really just the estimators and the equations in our 2014 paper implemented in Google Earth Engine. And there is a paper that we wrote a couple of years ago now, 3 or 4 years ago. I think Paolo Arevalo at BU, he is the primary author. Eric Bullock and me were co-authors. That describes all the different Google Earth Engine application that we developed, including this so-called Area 2 application that helps with sampling and estimators. I can see if I can find that.
Yeah, that would be awesome. And then as another follow-up question, I guess, I'm not sure who put this sticky note in, but that was sort of my main question was, Pontus, obviously you've done a lot of awesome work on like evaluating the accuracy of an existing map, but I was curious if those conclusions can be applied when you're creating, or if that same methodology can be applied when you're collecting reference data to train a machine learning classifier and create a product from scratch. So I'm not aware of any literature out there that has ways to do that, or if you can just follow the same methodology that you use to evaluate the accuracy of an existing map.
Yeah, I think so. When we talk about estimating things like accuracy and area and stuff, we are working under this statistical framework called the sign-based inference, and we have to draw a so-called probability sample, and we do that by randomizing the selection of sampling units. If we don't do that, we can't use that particular framework. We don't have that requirement when we collect training data typically. So we have much more freedom to do what we want, which is good in some way. It can be complicated in other ways. When I was at BU, we had a big measures project where we did global, I'm still doing it, there's continuation of that, global land cover change. And we spend a lot of time trying to figure out how to best collect training data. And there is a paper published in the Nature Scientific Data, I think it is, that outlines how to best do that, or not how to best do that, just outlining the lessons that we learned, at least when it comes to collecting training data for, here, I have it here. Radost Stanimiroba is the lead author of that. So that paper has some lessons learned, lessons that we learned for how to optimize the collection of training data. It also presents the whole training data set, the global training data set of, I think, 2 million training data locations with the labels. So I'm not an expert at all in providing generic guidance for how to collect training data, but this is, what's in that paper is what I know, kind of.
Got it. Yeah, thank you so much for sharing that. I'll also share the literature I collected at the end, and we've already got a great list of papers coming in, so we can get sort of a repository of resources for folks to go through. Yeah, Ate, please go ahead.
Yeah, since Emil put Pontus on the spot, we also have a question. An issue we often run into is that when we do area calculations for smaller strata, so think, for example, about deforestation, which is typically quite small compared to the total area, The error bars quickly explode when we find the positive sample inside the forest that wasn't classified as deforestation. So we have tried to work with buffer strata. I think that's also presented in one of your papers. We also create separate strata for areas with higher uncertainty. But I'm wondering if there are specific tricks, other tricks that we could apply to prevent these error bars from exploding too quickly.
Yes, you're referring to situations when you're trying to estimate something that is a very, very small proportion of the landscape, and you try to do that under stratified random sampling, and so certain omission errors can be very problematic. So if you have an observation of for example, deforestation in a very, very large stratum, that sampling unit will carry a lot of weight simply because it ends up, it's located in a big stratum. So I think the short answer is just if we could try to decrease the weight of the stratum in which this error occurs, then we could do a lot. And we try to do that with buffer strata. So we would try to, if forest is 80% of your study area, so the weight of the forest stratum is 0.8, you want to somehow identify substrata that are likely to contain the errors that are much, much smaller. And that's the idea behind these so-called buffer strata. Another idea is to just simply resort to simple random sampling. Then you don't have that issue. And you might end up with a very big sample size, but that would, at least you wouldn't have the issue of omission errors carrying large area weights. So those are kind of the two approaches that I'm aware of. One, try to break up big strata, typically a forest stratum, into substrata that are much, much smaller and more likely to contain the errors. That ought to be quite efficient if you can do that in some intelligent way, or just resort to simple random sampling.
Thank you. Yeah, that's extremely useful. That's also what we've been trying to do, but especially with deforestation, which is typically very, very small, even when the buffer strata can be quite large. So it remains complicated.
All right. I think unless there are any final questions or thoughts on this one, we can go ahead and move to the next question, which is a probability sample design necessary for training a machine learning algorithm? And so a probability sample design means that the inclusion probability, which is the likelihood of a given, unit, of a given unit being included in the sample, that inclusion probability must be known for each unit selected in the sample, and the inclusion probability must be greater than 0 for all units in the ROI. So that is, as I understand it, correct me if I'm wrong, but as I understand it, that's really important when you're evaluating the accuracy of a land cover product. But is that necessary when you're training a machine learning algorithm? Is a question that I don't have the answer to. So,
yes, as far as I understand, the answer to that would be no. If you want to apply the estimators in let's talk about my papers, but the books that I made use of in my paper, those require a probability sample, and design-based inference require probability sampling. There are other inference frameworks that don't require that, but when you're training an algorithm, there ought to be no such requirements.
Got it. So the next question, if I can find my cursor, is should the same imagery used for modeling be made available to the labeling process? So this is something that I've always heard is yes, whatever imagery you give to the model should be available when you're conducting the image interpretation project. But I was wondering if anybody has any perspectives as to why exactly that is, other than it just makes sense. I see someone put a sticky note in here about Professor Ian Woodhouse. Go ahead, Emil.
Yeah, I was the one who posted that. So back in February, Ian, who I think most people will recall from his authorship of the most cited book about SAR from 2005, he posted an interesting case from a remote sensing textbook that he had access to, where I think like lots of people, when you have training data of some sort, people generally divide the training data into two samples. Probably they do like a 70-30 or an 80-20 split, where they said, I'm going to use some of the training data to train the machine learning model, and I'll use the other, smaller proportion for validating, the outputs of the mapping. And then he cited, this textbook that was saying, actually just use all your training data model. And he said there are other ways to get at, what the error of the model, what the outputs are. And then, of course, since we have real life statisticians on this call, I'm sure that that some of the others might have thoughts on that. But do check out the thread on Twitter there of people, talking about, I think most people are attuned to, or most people have been brought up, trained, as it were, to learn that, you should do 70-30 or, 60-40 or 80-20. But, he was kind of challenging that based on, again, what other, experts in the field think about that. So yeah, back to you.
Yeah, that was actually, I actually had the 70-30 question as a separate discussion here. So thank you for bringing that up, because I actually took it out, but I was curious about that as to why I always see 70-30. So that's really interesting. I'll check that out. Any other thoughts on this question before we go forward? So this question has to deal with has to do with the size of the assessment unit. So let's say we want to train a machine learning classifier using Sentinel-1 and Landsat imagery, and maybe we also have a DEM, and all of these are different resolutions. One is 10 meters, one is 30 meters, one is 90 meters. What size assessment unit should I use when you're collecting reference data? Should it match the resolution of the data input to the model? Should it be matching the coarsest resolution data? Should it be 90 meters? Or is it okay to collect reference data about a smaller resolution size? And then the follow-on question to that is, do you need to rescale your input data? Should it all be the same scale when you're actually feeding the input data to the model? So this is kind of a two-part question. And again, here, I wasn't able to find anything in the brief literature review I did about matching the size of the spatial assessment unit to the resolution of the data you're using. So any perspectives on this question here? Hearing none, I guess we can keep thinking about this as we continue to design projects. So I forgot to add my visual aid here. Yeah, Emil, go ahead.
Yeah, if we could kind of move back to that question, just to say, I don't have a particular answer to that, but two people who are on the call right now, Betsy, from some of the work that she and colleagues did in mapping ecosystems in Central America a decade ago, and also Christian, who's joining us from CATIE. So I believe that the work that Betsy was doing, the protocol that they were taking for identifying, units out in the field, essentially they were trying to and again, Betsy, feel free to chime in, and also perhaps Christian. Long story short, CATIE, where Christian works, had come up with a method that kind of said, if you're going to look at, the accuracy of MODIS data, then it doesn't make sense to, pick really small things, and then you say, hey, but, this tiny sample that I found in the field doesn't match the 250 or 500 meter pixel, right? There's a documentation that CATIE and others had put together, but I didn't know if maybe Betsy or Christian wanted to speak to that. Putting people on the spot. I'm not sure if maybe Betsy has mic issues, but Betsy, go ahead.
Yeah, thank you, Emil. I don't remember right now about that reference, but yeah, you are correct. Just taking one sample from the field obviously doesn't represent, for example, if you are using MODIS data for the whole area. But let me check again on that reference as well, because we were using, I think, Chubieco, that is in Spanish. I don't know if you have heard about him. He is a really known remote sensing expert from Spain, and I think he has that reference about how to take samples. Yeah, thank you, Roman.
Yeah, and I might just not to beat a dead horse, but I might be, hopefully I didn't put Christian on the spot, but I do recall the methodology that Katia had put together. This was like maybe 2005, 2006. Also accounted for things that are too close to other land cover types and positional errors. So like in the GPSs, I guess in the past also had greater positional errors than they do now, and so the idea also of, let's say you're validating a land cover map based off of Landsat or something like that, that it's also good to get these big homogeneous, areas that at least meet the size of a few Landsat pixels. And also when you're collecting those samples, making sure that it's not too close within the range of the error of the GPS. Therefore, you might be picking up something that, you picked up a field, but the GPS, signal is slightly off, or as it were, or there's an error as it were. And so, you pick up this coordinate and the coordinate actually is corresponding to the forested pixel right next to you. And so, really great question, Mickey. And then I think I'll stop there and just say, I'll look up the report that Katia did put together on that Betsy and colleagues used in their field work. And I can share that in the chat. Or I see Kristen has his hand up. Thank you, Kristen.
Hi, Emil. Hi to everyone. My name is Christian from Cati in Costa Rica. I tried to remember what was the protocol from map to the El Salvador. I have an example. I need to pick the document. I will to try to share to us, but I need to read. But I remember that we take 40 or 50 samples for land cover into the El Salvador, Guatemala, Honduras. But let me to find the document. I will to share to us. Okay. Give me a second, okay?
That would be great, yeah. So the next, also Tim and Biplov, let me know if you wanted to reserve some time at the end. It's probably not likely that we can get through all of these questions anyways.
No, we don't have anything at the end. Feel free to,
okay.
The clock's all yours, Mickey.
Gotcha. So the next question is relating to the response design again. So maybe I can make a little drawing here since I forgot to add my visual. But basically this has to do with mixed assessment units. So what if our assessment unit is 1/2 water and 1/2 trees? Should we consider that unit as trees if we're training a machine learning model, or should we only feed what's called pure assessment units into the model? Should we only feed assessment units that are 100% that land cover class? Or is it acceptable to do 90%? Is there sort of a standard, a gold standard in the field for collecting assessment units to feed to supervised classifiers? I wasn't able to find anything in my literature review. I've heard just sort of in discussions that pure pixels are obviously better, but I haven't come across any sort of gold standard for 90% is good enough, or you should only use 100%. So curious if anybody has any thoughts there. And I see someone posted in the chat. Yeah, and I'll work to collate these resources later, as I said. So thank you all for sharing those in the chat. Yeah, Tim, go ahead.
Yeah, I mean, I don't have a definitive answer, but this is, I think it prompts an interesting question from like the, if you couple both the data collection side and then also what you're actually wanting to model. Because I think if you look at are you just trying to do a pixel classification and all you're really interested in is like a binary output, essentially, I would imagine if that's the case, you're going to want to find the most representative pixels possible, the 100% of that class, 100% water, 100%, desert, shrub steppe, what have you. But if you're actually interested in like a regression, you're trying to understand what the canopy cover is, and that fraction is important to you, then the more mixed the pixels are, I think it would be more important to the model, right? Because you're interpreting the landscape more effectively. You're actually getting at a continuous response. So like having representative pixels of the landscape that capture all of that is probably the best approach. But that also then like magnifies your challenge, right? You have to find pixels at 10%, 20%, 30%, or whatever those bins are. So I'm sure there is a heuristic for this, but I always kind of trace my approach back to, what is the modeling that I eventually want to do? And then that will inform the data collection process too. So it's just some of my musings. I don't know if other people have thoughts on that.
Yeah, that's a really awesome point. I was just approaching it from the binary perspective. So thanks for sharing the regression perspective. And just like in my experience, which is limited, but still in my experience, I struggled to find areas where 100% is one land cover class if you're using an assessment unit of like 30 meters. So that's what sort of prompted this question. So going once, going twice, any other perspectives on that? If not, we can jump to this, which we kind of touched on a little bit earlier. But if a random stratified sample is performed using land cover class as the strata, what allocation should we use to train a machine learning classifier? Earlier, we talked about how that hybrid allocation, where you have a certain amount of points allocated to each class, but then undergo proportional allocation. That's the recommended strategy for evaluating the accuracy. But I'm curious for perspectives for training a classifier. Should we give the model the same number of sample points for each land cover class, or provide more samples of rarer classes, or the other way around? Any perspectives there? Again, these questions kind of get more rhetorical as we go on, so there may not be a right answer. Yeah, go ahead, Tim.
Yeah, I'm full of the no right answers or no definitive answers, but it's an interesting question because I think, it assumes that there's maybe I'm I'm exposing myself here that like, oh, there's one definitive method, but I find that like doing this iterative modeling process and tuning different features, like as you're trying to identify a really sparse class, like what Ate had mentioned, there's some challenges in trying to identify a deforested class which happens to be sparse. So your proportion of sampling that you may want to have that to be really, really high relative to the others, because that's the feature that you're actually interested in. But it may actually introduce way more bias. So that's something to be cautious about, I would think, that you need to weigh. I don't have the hard and fast rule, unfortunately, but it's something that I'm constantly thinking about. And I know for a lot of people on this call who spent time doing rice mapping in Bhutan, that was something we talked about a lot. It's like a really, really tiny class, a really small feature on the landscape. How do you effectively model that? So we took this strategy of doing exhaustive sampling almost, really identifying that and trying to find mixed pixels and 100% pixels because that was such a sparse class. And we went through that process by doing, iterative, trying to improve our accuracy as we went. So I wouldn't say that's the best way to do it, but that's the way we did it. Other people have thoughts?
Go ahead, Emil.
Yeah, I guess just in response to what Tim was saying, I definitely see what Tim is saying. I've also often wondered, especially with some of the different, machine learning, the classification algorithms that we're using, where you usually have to select a parameter of, is what you're classifying, should you use the same distribution from your training samples to map that out to the land cover classes? I've often, and I haven't, I have definitely not dived into that, but kind of wondered how the outputs would differ if we say, all right, yes, choose the distribution based off of the distribution from the sample, or you go with some of the other options, how that would then kind of skew what it's mapping as one class versus the other. Like, I remember in the old days, when we were using Envy for doing classifications, that was definitely one of the options that you could pick, saying, okay, if I had, 60% forest in my training samples, should the output also match that it's roughly 60%, or is it, just, assigned based on whatever? So I also don't know the answer to that question, but would hope that maybe this working group, that's something that we could look at in the future. Over. Thank you.
Thanks, Emil. And yeah, I think Tim brought up a really good point of it might just depend on what your objectives are. In the binary case, it may be much different than if you're creating a generalized land cover map. So I haven't found an answer, but maybe there is an answer out there for like a gold standard way to do it, or people comparing different allocation strategies. Maybe we can find out that answer if there is one. So let's see, we're at 5 minutes to go. So maybe I'll find the most intriguing question as our last one, or one of our last one. Let's see here. I guess this is a question that I'm really interested in, and one that Tim actually asked again when we were doing the Bhutan work. But, when we're feeding imagery to, let's say we want to create a model that represents conditions in 2021 as a whole, or the leaf on period in 2021. Should we, if we have a time series of imagery, should we even reduce that imagery at all, or should we pick a single image to use? And if we do reduce it, what allocation strategy what reducer should we use to take that time series imagery and represent it as a single image? And then a related question is, if you're doing for the whole year, should you use a composite that covers the entire year? Should you use just the leaf on period or the leaf off period? Again, this is probably one of those questions that there's no gold standard for, and people just pursue a different strategy depending on their objectives. But I'm curious if there's any perspectives there. Yeah, go ahead, Emil.
Yeah, at least on the question regarding the reducer, at least in my own limited experience, I've tended to use a median reducer, and I've also, though, tended to limit the images that I'm looking at to dry season imagery, specifically where, with SERVIR hubs, we're, working with tropical regions that have cloud cover. If you use like a minimum or a maximum, and you think of the potential impact of cloud cover, even if you're using, cloud masks, Landsat automatic cloud masks or Sentinel-2 cloud masks, etc., the minimum has the effect of it's going to pick the pixel with the lowest value. And so what that usually will pick up is cloud shadow. And if you use a maximum, that will pick up the cloud itself. But then also, if you're limiting yourself just to that dry season when the likelihood of having a cloud in a pixel is lower, found that the median is, gives you a cleaner result. But other people might have different kinds of things. But in the past, I also definitely played around with, the multiple options, and I was like, okay, let's do a minimum. And then I ended up with lots of, dark pixels because I was picking up cloud shadows. For some areas, say maximum, end up with, really white image because you pick up the actual cloud. Median seems to work well. I know that other people like the FAO folks and even Robert Kennedy for his Land Trender, compositing algorithm, He uses the medioid, which I guess is similar to a median, but I'll stop there. Back to you.
Yeah, thanks, Emil. Go ahead, Tim.
Yeah, this is such a practical question, right? Because this is the stuff you'll be doing day to day, right? Making these decisions and justifying it. I think it's really it's about your target, right? So if you're trying to identify water bodies, you might choose a different approach as if you're trying to identify, tree canopy, right? Those decisions I think are going to weight, your targets are going to weight your decisions in some way. And I also, I know we're at almost at the top of the hour, but I also kind of want to posit the idea here that these are the rules for the tools that we have right now. But in the future, with like HLS informed foundational models, it's going to see all that data. It doesn't have to make decisions based off of how cloudy a pixel is and creating these different subcomposites. So I think this is, we might be on the cusp of a new frontier in that, because we'll have access to this whole archive. So just food for thought, and I'll go over to Stephanie.
Yeah, so I guess kind of along, or just in the new technology direction, thinking about like deep learning and, RAMI, specifically the radar mining tool in Amazonia that, augments the patches of imagery that they have, the sample sizes that they're training the models with by flipping the image and, twisting it, this, whatever goes on with augmenting it. But I don't know. I don't even know if this is really a question, but just kind of thinking about how do these recommendations and these sample sizes translate over to those scenarios and to those different classifiers that are technically looking at the same thing, technically sample sizes of the same region, but are being altered. So is that an addition of sample size, sample, or, I don't know. That wasn't really a question, but just thinking about the how that translates into that situation.
Yeah, it's a great question. I don't know the answer, like most of these questions, but hopefully this has been thought-provoking, and I'll share, maybe we can share a follow-up email with some literature for everyone to review. So thank you, everyone, for your perspectives, and sorry for going over time a little bit. Thank you, Tim and Biplav.